Alright guys, today we're going to talk about fluid flow continuity, which sounds very fancy, but it's really a pretty simple idea. It says if we have a pipe or a hose or something like that, and we have some mass of fluid entering one side, we're going to also have a mass of fluid going out the other side, and those two masses have to be the same. So the amount of fluid we pump in one side and the amount of fluid coming out the other has to be the same. That's the whole idea behind fluid flow continuity. So here we have a pipe 1, which is a larger pipe, and it's connected to pipe 2, which is a smaller pipe, and basically what we're saying is the rate of mass flow through pipe 1 and the rate of mass flow through pipe 2 have to be equal. So of course then it makes sense that the fluid, or we can think of it as water in this case, will have to flow faster in pipe 2 than it does in pipe 1. And that's why, as you guys all know, like if you have water coming out of the hose and you want it to spray out faster, you put your thumb over the end and make the opening smaller, and that makes the water come out faster. That's the whole big idea of fluid flow continuity. Okay? So delta M1 has to equal delta M2. The rate of mass going in pipe 1 has to equal the rate of mass going out pipe 2. Alright, and we can calculate the rate of mass flow through the pipe by taking the density of the fluid times the rate of volume flow through the pipe. And so the density of the fluid at point 1 times the rate of volume flow at point 1 equals the density of the fluid at point 2 times the rate of volume flow at point 2. Now, if this is a liquid, liquids are fairly incompressible, and so the density is never going to change, and we are always just going to do these problems with liquids, so we're never going to care about the density. If you're dealing with a gas, then it becomes a bit more complicated and above what we're doing for this class. Alright. So, the amount of volume that flows through a given pipe is actually equal to the cross-sectional area of the pipe times the speed of the fluid in the pipe times the time. And so we have to set those two equal to each other as well. And of course those two times are the same, so the time cancels out. And so we're left with our final equation, which is the cross-sectional area of pipe 1 times the speed of the fluid in pipe 1 has to equal the cross-sectional area of pipe 2 times the speed of the fluid in pipe 2. And so what we see then is that the bigger pipe that has the bigger cross-sectional area is going to have the slower moving fluid, and the smaller pipe that has the smaller cross-sectional area is going to have the faster moving fluid. Let's try a problem. Okay, for this problem we have a fire hose, and the diameter of that fire hose is 9.6 centimeters, and water is flowing through it at 1.3 meters per second. We have a nozzle on the end of the hose that has a diameter of only 2.5 centimeters, so we want to know what will be the speed of the water as it leaves the hose. First thing I'm going to do is write down my givens. Okay, so the speed at area 1, which we'll call the inside of the hose, was 1.3 meters per second. And I had to calculate area 1. A hose is circular in cross-section, so it's pi r squared. So pi times 9.6 over 2 squared comes out to 72.4 square centimeters. And then area 2 is going to be pi r2 squared, which is going to be pi times 2.5 over 2 squared, which comes out to 4.91 square centimeters. Now those are not standard units, but since a is on both sides of the equation, the units cancel out, so as long as a1 and a2 are in the same units, it doesn't matter what units they're in. They could even be inches or square feet or something like that. And we're solving for v2. So now I'm just going to set up my equation. So A1 V1 equals A2 V2. Rearrange for V2, and V2 is A1 V1 over A2. So now we just plug in and solve. So when I plug everything in, I get a speed of 19 meters per second, showing that the water comes out the end of the hose much faster than it's flowing through the hose because we have this small nozzle on the end of the hose making the opening smaller. Alright, so here's a problem for you to try. Okay, for your first problem on the Google form tonight, I want you guys to figure out if you have a pipe with a radius of 1 inch and water is traveling through it at a speed of 2 meters per second. And then at the end of the pipe we have a nozzle whose radius is only 1/4 of an inch. The pipe is horizontal, so the water squirts out horizontally from the end of the pipe, and it does that 2 meters above the ground. So I want you to figure out how far does that water travel in the horizontal direction before it strikes the ground. Okay, so we're taking our fluid flow continuity problem and we're combining that with a projectile motion problem that's horizontal launch. So good luck with that, and put your answer in Edmodo. Your answer should be in meters. Do not include units in your answer. Alright guys, the other thing we're going to talk about tonight is called Bernoulli's principle, or Bernoulli's equation goes with it, which basically says that as the height or the speed of a fluid goes up, the pressure of that fluid will go down. And you may notice that this term right here, 1/2 rho v squared, looks very similar to kinetic energy. And you may notice that this term right here, rho g y, or rho g h, somebody else might call it, looks very similar to gravitational potential energy. And Bernoulli's equation is very complicated to prove. We're not going to do it here, but it is an application of conservation of energy. So the pressure of a fluid plus 1/2 rho times the speed of the fluid plus rho times g times the height of the fluid will always be a constant. And since it's a constant, if we have a situation, two different situations we want to compare, we set those equal to each other. So the main way to see the equation is like this. So P1 plus 1/2 rho V1 squared plus rho g y1 equals P2 plus 1/2 rho V2 squared plus rho g y2. So let's apply this to a problem. Okay, so we have water flowing through a large pipe that's 2 meters below the ground at a speed of 2 meters per second. It flows up through a smaller pipe to ground level and comes out of that opening at a speed of 10 meters per second. Now, where the water comes out of the opening is open to the atmosphere, so the pressure there has to be 1.01 times 10 to the 5th pascals. So we want to know what is the pressure down in the pipe below the ground. Okay, so we have this distance here is 2 meters. And we're going to call the area down in the big pipe position 1. And we're going to call this at the opening, where it comes out of the smaller pipe at ground level, position 2. So let's set up our equation. So we're all set up. P1 plus 1/2 rho V1 squared plus rho g y1 equals P2 plus 1/2 rho V2 squared plus rho g y2. And we are solving for P1, so I'll go ahead and rearrange. And now I've rearranged my equation to solve for P1. All I have to do is plug in all the givens and solve. Okay, so we have 1.01 times 10 to the 5th plus 1/2 times 1,000 times 10 squared plus 1,000 times 10 times 2, if we call the height of the ground 2, minus 1/2 times 1,000 times 2 squared, which is the speed of the water in the pipe, minus 1,000 times 10 times 0. We're going to call 2 meters below the ground 0. Alternatively, we could have called the ground 0 and 2 meters below the ground -2. And this right here should say minus, not plus. Alright, so plug all that in. So when we plug all that in, I get that P1 equals 1.69 times 10 to the 5th newtons. And so what we see is that the pressure down in the lower, slower moving water is greater, which is exactly what we would expect. Now it's time for you to try one. Alright guys, so this problem actually uses both concepts we've learned tonight. We have water traveling at 1.2 meters per second with a pressure of 143,000 pascals. It travels up a step that's 0.20 meters high and then is connected into a smaller hose that has half the cross-sectional area of the original hose. So I'm going to get you to do two things. One, use your fluid flow continuity to figure out what is the speed of the water in that second hose with half the cross-sectional area. And then part B, what is the pressure of the water in that second hose with half the cross-sectional area. So give that a go tonight, put your answer into the Google form, and we will go over these problems tomorrow and look at some example free response problems. I'll see you then.